Hi, Chris DeLeon here once again. This is video 2 in the introductory series for programming and processing to make real-time interactive programs where you can have real-time input to them and they'll move graphics around. We're going to be in processing again, although we're going to start from new. We don't want to open up the last example we worked on. We haven't really written substantial enough code yet to worry about needing to build upon it or to save what we'd worked on. So let's start a new one. And again, I'm kind of assuming that if you're following this introductory series, that you're maybe new to processing and you may still have questions about its place in the ecosystem of programming environments. I had a little bit of information about that in video 1. We also covered how to install processing, how to use comments, the basics of, like, say, the draw, setup functions, and graphical coordinates. But I want to add a little more detail now to far as why we're using processing and what else we might still use it for. So you probably haven't used finished software made in processing. Games made in processing don't really get sold or distributed. Software written in processing doesn't tend to get distributed except within academic circles for demonstrations. But as a learning environment, it's great because it's not just really quick and easy to set up with no complication. So if we tried to all get everyone on the same page of using SDL and C++, there's a lot of barriers to getting your environment set up for that. If we all try to use ActionScript 3 to write Flash applications, we've got issues trying to get that stuff into mobile platforms for 1 and for 2. There's just sort of this awkward change that happens each time they change the versions, and basically this is just a good setting for learning programming, but more specifically it's one which structurally has so much in common with all those other environments of C++ and ActionScript 3, of JavaScript games, of sort of a whole family of languages written around the same structures and the same coding practices and the same concepts as we're going to cover in processing. So it's not like a strictly learning environment where everything gets simplified and there's too much hand-holding. With the information you're learning here, with a little bit of additional work to set up or a little additional work at the end to distribute, are really things you're still going to find yourself doing in other platforms. And that's something that I'm coming into this. I've been writing programs for now about 15 years. I know about a dozen platforms for development, and out of them, I still use processing for certain support applications. I've used it for a research project, doing an animation tool. Used it for another research project that compiled exported animations into a sprite sheet, as well as use it for demonstrations of code because of its sort of ease of use to get into it and to make sense of it, and again, its structural similarity to the other languages. But without further ado, let's get back to programming. The first things that we're always going to write in every processing application are a void setup and a void draw. Again, just as a reminder from last time in case you took a break between the two. Void setup gets called once when the program starts. Void draw will be called repeatedly every time the frame updates. And it's not just for drawing, it's also for where we're going to handle cycle by cycle, frame by frame logic in the application. You'll sometimes hear me say game instead of application, kind of one or the other. Again, my background's in games, so that's often what's on my mind. But in fairness, processing can be used for all kinds of non-game, interactive, real-time, expressive applications and environments. So here in void setup, one call we're almost always going to do is setting up the resolution for our view. And as a reminder again from last time, that comma does not indicate 720,400. It's separating two parameters or two arguments for the size function. 720 is our width in pixels, 400 is our height. You can set these to any numbers you want as long as they fit on your screen. But I choose these numbers because they fit nicely here under the video on my screen, so you can see what's going on there as we make changes. And of course, when we make changes over here, they will not be immediately reflected down in the sketch. For that, we're going to have to stop it and press play to see them again. As a quick rehash of some of the stuff we did last time, because we're going to build on some of those ideas, we can do a rect, mouse X, mouse Y, 40, 40. That will draw a rectangle where the mouse currently is, which we can then move around and smear. We can get away from that fact that it's smearing by redrawing part of the screen. And so if we redraw the top left corner, for example, here we've got a rectangle from the corner 0, 0, the very top left, half the width and half the height of our window. You'll see here there's no smearing, and over here there still is. It's just the fact that each frame, this rectangle up here, the big one's being redrawn, and so it's hiding the fact that or basically it's clearing the frame buffer from where previously it accumulates. We could make that a rect call that covers the whole dimensions of the screen and get that same effect. But kind of the proper way to do this and it makes it easier for us to set the color for it, is instead to make a background call with 3 values for red, green, and blue. So here, sorry about that, we've got full red, full green, I'm sorry, 0 red, 0 green, full blue. And that'll give us a deep blue background, and that's going to keep us from seeing the accumulated image buffer. Now we've been using rect so far to draw rectangles, say where the mouse is or where predefined coordinates are. But if instead we say ellipse, it works exactly like rectangle. It's still an x and a y coordinate and a width and a height for the ellipse. So when I press play, you'll see now we have an ellipse. Now notice too that whereas the rectangle, first 2 arguments, the x and the y, were used for the horizontal and vertical position of the top left corner of the rectangle, for the ellipse it's actually the center point that's being set. Notice that. So for example, if we wanted the hard code coordinates, let's say we have an ellipse that's 80 by 80, and of course if we make the width and height uneven, we'll just get a stretched oval as opposed to a circle. If we wanted to center or like push this up against the corner, then here you'll see the center is 40 pixels in and 40 pixels down, and 80 pixels wide and 80 pixels tall. So that's the center point and the full width and the full height, or diameter if you will, rather than say a radius. Now let's get that thing to move around, kind of on its own. For starters, let's put it up in the corner. Let's make the ball smaller. Oops. 5 pixels from the side, 5 pixels from the top, 5 pixels by 5 pixels. That'll give us a smaller ball. That's a little too small maybe. Let's move it away from the wall, make it 15 by 15. You'll see in a bit why I want to keep it small for now. There we go. Okay, so we're going to make that white ball move on its own. So last time we created some variables doing things like int, and we would say like ball size equals 15. And that would make it so anytime we wanted to change one number or change it in both locations, and we could also keep track of what these numbers meant, we could just change it where this label was. When we do a variable here within a function, when I say within or inside of a function, I mean between the braces. That's something we refer to as scope in programming. This sort of gets created and destroyed within that scope, and by the time draw gets called again, it gets forgotten. And so what I mean by that, for example, is that if I say, let me scroll this down so you can see more of the window at a time. If I say ball size, it's actually something we're going to have to explain here in a second. So if I want to increase the size of ball, I could say ball size equals 20. And so even though it was 15 when we declared it, it's now 20 after this line. And so this will draw a ball which is 20 pixels by 20 pixels. Maybe a subtle difference. Let's make that a little bigger. Now you'll definitely notice that it's 200 and definitely not 15 pixels wide and tall. Now an equal sign in programming, as you may have noticed, doesn't work like it does in algebra. This isn't a statement of equality in the sense of it's a balanced equation. What's happening is whatever is on the right-hand side gets evaluated and then assigned into the label on the left-hand side. And so we don't actually have to say 200. We could say 100 times 2. It would do this computation, and it would change the value of ball size. Now, one weirdness about this is that means that if we want to change ball size relative to what it was, let's say we'll make it 5 more than it was, then we actually write this thing, which again in algebra doesn't make any sense, but in programming you get used to, which is to say on the right-hand side, ball size, which was 15, we're going to add 5 to it, making it 20, and then we're going to assign it back into ball size, so that down here we're down to 20. But again, let's make that difference more dramatic so we can really see the difference. Let's make this 85, so now we're up to 85 plus 15, 100. So ball size, which was 15, plus 85, it's going to save it as print line 100. And we're going to print line it, so you're also going to see it down here in the console, proving to us that it is, in fact, 100. So you can see down here the 100 is being printed every draw frame. You can see that ball is about 100 pixels wide. Now, even though we're adding 85 to it, the next time draw gets called, it comes back around to the top of the function. It's starting again, redeclaring that int ball size is 15. And it doesn't remember that we previously have added 85 to it. It's resetting it to 15 each time. A way we can make it accumulate is I'm going to move that declaration of the variable out of draw, outside of setup as well. It's just going to be floating in what we call the global space, where the outside of the functions. And now I'm going to make this change more subtle. So instead of adding 85, I'm going to add 2, and you're going to see why. Because now it's just going to continually grow. And you'll see down here, when we print out ball size, it keeps getting bigger by 2 pixels at a time. And the reason for that is because now the variable is declared outside of void draw. It was 15 when the program starts. The code gets to this point, and if we scroll all the way up, we'll see the initial value it was set to was 17. Because it was 15, so ball size was 15. We added 2, so now it's 17. We assigned it, it always assigns going left, to ball size. The first time we print it, it's already 17. We're drawing it with those values for the dimensions. And then when it gets back around to draw, you'll notice that we're no longer resetting or redeclaring it to 15. It exists kind of outside this function's scope. And so when I say ball size equals ball size plus 2, it's taking the value it previously was left at, 17, adding 2, making it 19, saving that into the label, so we're up to 19 now, and print line, and so on and so forth. Now instead of assigning these to the diameter of the ball to keep it changing size, let's make one we call ball position X. And instead of changing ball size each frame, let's change ball position X each frame. I'm going to get rid of this print line because I don't think we need it anymore. Okay? And now you'll notice that I'm leaving ball size out here, even though we're not changing it. It would be kind of nice and organizational to put it inside of this function, since we're just kind of using it as a one-off label. Another approach, though, to programming these things, so let me move setup down below. So the order of functions that they're declared in doesn't actually matter, because they're not being called based on the order in which they're declared or defined. Setup is always going to be the entry point of code, from the top brace down to the bottom brace, and draw will always happen repeatedly. Soon we're going to start adding our own other functions, and those will only get called if we call it from setup or from draw, or from some other function called from setup or draw. But the flow of code doesn't actually have to do with the order in which we define those functions. So one approach to programming is that when we pull these variables out, like ball size, we can kind of put them all at the top of the program, and that makes it easy for us to look at this program and modify it without having to look down below about how and where these things are working. So here we've got ball position X is starting at 15, ball size is 15 as well. If I want to change the ball size, I can make that 30, and without changing anything else below, I know that I've just redefined the ball size, and I can count on the fact that when I use that number, I put it in places that expected that to kind of like compute based on the size of the ball. But okay, so going back to what we were doing, ball position was 15. In the very first frame, it's going to add 2 to it, so it's going to be 17, then 19. It's going to count up these same numbers that we saw before when we were increasing ball size. But instead, that's going to be used as a horizontal position for the ellipse. So of course, as you might expect, it's traveling across the screen. Because remember, draw is being called many times per second, and there it goes. And each time, that number in memory is increasing by 2. And so if we said plus 1, it would decrease by a less amount. Now I will say that this particular construction that you're seeing here of ball position X equals ball position X plus 1 is such a common construction in programming that there's shortcuts to do it. So a general case of if we want to add 2 to a number in memory is we can take the label and say plus equals 2, which means to add 2 to whatever it was and save it back to the number. This plus equals is, again, kind of takes some getting used to. Minus equals also works if we want the ball to go backwards. Times equal also works if we wanted to make the ball move exponentially fast, and we can actually see that. It's going to be very quick, though. Room. There it goes. Divided by equals 2 will make the ball retreat by division. Again, very rapid. But those are ways we can add, say, 5 pixels to it every frame. It'll just race along and go off the screen. There it goes. And in fact, plus equals 1 is so frequent in construction that a shortcut for that is to just say plus plus. This is saying to take the value that was in ball position X, add 1 to it. This only works for adding exactly 1, or subtracting exactly 1 if we use minus minus. Take the value that was in ball position X, add 1 to it, save it back into that position. So at first it was 15, then it's going to be 16, 17, 18, and so on. And again, we get this ball crawling across the screen. But just to be clear, because you're going to be seeing these kind of constructions all over the code, that, I'm going to use a comment here to write code that you can't see, or that the program won't see, is the same as that, is the same as that. And one of the things you're going to get used to in programming is that there's often many different ways to write the same functionality. It becomes a matter of programmer style choice, or a matter of communicating with clarity to yourself in the future, if not even other programmers, what your intention was in a way which is readable without being too sort of buried and obfuscated. But in this case, this is such a common construction, you'll get used to seeing that plus plus frequently. So we have a ball that's moving. Now let's say we want the ball to reverse, because right now it goes right off the screen. Let's speed it up so we can see it go off the screen. Plus equals 7. It'll move 7 pixels at a time. Now notice that in order to make the ball move, we had to create a variable to keep track of it. And that's because the ball's position is changing. When we just gave this a fixed number, let's say we just make this 60, notice now we're not even using this variable. We're still adding 7 to it, we're not even using it. The ball is just going to stay at 60 because that's the position we're drawing it at. We created a variable to use for the position strictly because we want to be able to change it. And so likewise, the ball currently is always moving to the right at 7 pixels every update. But if we want to change that so we can occasionally make it go negative 7 pixels per update to bounce backwards, then we might create a new integer, ball move x. Let's make that positive 7 at first. Now first of all, just to step back through what's going on here again, we're asking the computer to keep track of an integer, so a whole number, positive, negative, or 0, just no fractional, no decimal points. Labeled ball move x, and once again, just like ball size and ball position x, the program doesn't understand the term ball, the term move, or even the fact that there's an x there to mean horizontal. Those are strictly conventions that we're using in choosing how to name this. If we named this envelope, or if we named it honey, it would do exactly the same thing as long as we put those labels in the same places. But it's good programming practice to stick to labels that are descriptive of what you're going to use it for. So we're going to have a label for ball move x, which starts out at 7, and we're going to move the ball by that amount. Now what we need to check is, if the ball moves off the right side of the screen, we're going to flip that number so it goes back the other direction. If, I like to copy and paste variable names as a way to avoid typos. If the ball's position is greater than width. Now remember that in processing, width is automatically being set when we declare the size of our window. So width here is 720, and you could print line that if you want to double check that. When the ball's position, the center of it, goes past the width of the screen, then we're going to change the value of ball move x to negative 7. Now notice that once again, because we've declared the variable outside the scope of draw, anytime we make a change to it, it's going to persist beyond the scope of the draw function. So as soon as the ball goes right of the screen, we're going to flip that value to negative 7, and suddenly when we get to the next draw call, it's going to be moving, it's going to be adding negative 7, which means moving it backwards from the way it was going. And we can watch this happen. Goes to the right, bounces left, and of course we're not handling going off the other side, so we could write a condition for that. If ball position x is less than 0, 0 always being the left edge of the screen, then we're going to change that speed to positive 7, and we now get a ball that bounces back and forth. Back and forth. Now these ifs I've just sort of thrown in there. I think they can be a little wonky if you're new to them, but they're not as complicated as they might seem. All we're doing is we're asserting if the following expression checks out, if it's true that the value behind this label is greater than the value of that label, then whatever code's between these braces happens, will take place. Otherwise, it gets skipped. So for most calls of the program, this isn't happening and this isn't happening. And so we can even put a print line there as proof to ourselves. Bounce off right edge. I'm going to put another one of those down here. Bounce off left edge. I'm going to press play. Watch the console. Bounce off right edge. Bounce off left edge. Bounce off right edge. Bounce off left edge. And so this code is only happening the very frame that the ball is moved too far right, and the very frame that the ball is moved too far left. And again, we're not changing the ball's position here. All we're changing is the ball's heading to go either making it move left or making it move right. You will find out from other programmers or from looking at other programmers' code that when an if only has one line of functionality, you technically don't need the braces. You can get away with not having them. It'll assume that the up until the next semicolon is all that goes with that if statement. Something I learned from a Google engineer I used to work with, former Google engineer, is to always use the braces even for a one-line if statement, because what happens if you don't do that is at some point you might come along and try to add code here. Bounce off right edge. And of course, since this is not within braces, and without braces it only means up to the next semicolon, even though we've indented, remember white space means nothing to the program, this second line we've added will actually be called constantly because it's not a part of that if. What we probably intended by that was this, and to make that explicit, it's good to have those braces there from the very beginning. Okay, so we've got a ball that bounces left to right. Now the next thing that I want you to do, to see if you can follow the pattern that we had so far, is can you add some code. You're going to have to create a new variable or two. You're going to have to change some values in the current program to make this ball also bounce not just left to right, but also up and down, so it'll travel a diagonal path around the frame of the window that we're in. And again, if you haven't downloaded processing yet, please go to processing.org and download it. It's free. It's not a huge file. It doesn't take long at all. And there's no setup required. You just basically run it once you've unzipped it. If you have not opened processing yet, I encourage you to open it and follow along. Copy down the code we have. There's not so much so far. In fact, there's only 23 lines of code. Let me help review what we have. Declare the variables at the top, globally, in this case. We have a void draw, setting the background, moving the ball, yada yada. But basically, it's not that much code. You should really try out this exercise. Can you pause this video and change the program to make the ball not just bounce left to right, but also up and down in addition to left and right? Pause the video right now and try it. Come back, and I'll show you the answer. You'll get a lot more out of this if you try it yourself. Go ahead. Okay. And I'm counting on the fact you've done it, so if you haven't yet, spoiler alert. Simplest way we might do this. By the way, if you do have some programming background, you might be wondering, why is this not in a class? Why are we not handling this with an object-oriented fashion? We're going to get to all that, but for starters, I find that just keeping things simple to variables in one file at first can help the concepts kind of be more evident and not introduce too much at once, but we will move towards organizing our code better very soon. So, an easy way to get the X and Y movement doing the same kind of things is to, well, basically let's duplicate the fact that we're going to have to change the Y position, so we know we're going to need a ball position Y variable. We're going to change the heading of it, so we're now going to need a ball move Y or ball velocity Y variable as well, so that it can be heading one direction and then change when it exceeds the other boundary. We can probably suspect it's going to look a lot like our ball X code, and we'd be right about that. I'm actually just going to duplicate it, replace those X's with Y's, replace that width with height, because now it's a question of, did the ball go off the bottom of the screen? Remember, Y-axis goes down in programming. Most programming environments, at least. Changing those X's to Y's. So each frame, it's going to move the ball by its current Y velocity. If the ball goes off the bottom of the screen, it's going to make its Y velocity negative. If the ball goes off the top of the screen, it's going to make the Y velocity positive. It's going to keep it bouncing towards the middle of the screen. And we can't forget that we also need to use this ball position Y variable as the coordinate for the ball. Otherwise, we've kind of wasted our effort. Because if we set the fixed number, it doesn't matter we're changing this number in memory, because we're not using it to position the ellipse on the screen. So again, to review those changes, I added these two new variables, just like we had for X. I duplicated the way we move the X coordinate and checked for the edges. Did the same thing for Y. Don't forget to change the width to height. And for the Y coordinate of the ball, set it to this new variable we're keeping track of for the ball's Y position. And sure enough, we now have this simple ball which will bounce around the screen. Now, one reason why we wanted to start off with a simple ball, and this is leading to another exercise, or a rather small ball, is because we're, of course, actually checking the center coordinate of the ball, the very center point of it. And so what happens if we make the ball bigger, let's change that ball size to, I don't know, 100. It becomes more evident that the ball is going half off the screen when it bounces. So what I want you to try to experiment with next, again if you'll pause the video for a moment, is to modify your conditions for your edge checks so that the ball will not leave the screen even partially, but will kind of like account for its ball size. So if we make the ball 200, and press play, your goal is to keep the ball bouncing off the edges. With your value starting around here, go ahead and make your change to your code, pause the video. It's going to involve changing these conditionals to account for ball size. Give you a little break for that. And we're back. Really hope you're taking the time to try this. I think you're going to get a lot more out of it if you do. But if you want to follow along, it's up to you. So I'm going to take that ball size, and since the center is ball position X, what we really want to check is to see if ball position X plus half the ball size goes off the width of the screen. Because remember that ball size is being used for the total width and the total height of the ball. And so maybe another way to phrase that so we can avoid doing this calculation all over the place is I'm going to create a new variable called ball radius as half the ball size. And this will avoid me from having to remember to do that divided by 2 all over the place. So if the ball's position plus the radius is greater than the width, then we're going to make it go backwards. And if the ball's radius minus the ball's position to the left edge of the ball goes less than 0, then we're going to make it go to the right. And we can reverse these, just like any other expression you might deal with in math. We have, instead of adding ball radius here, we could subtract ball radius there. Instead of subtracting ball radius from the left side, we could add ball radius to the right side. Same end results. Some programmers, myself included, prefer oftentimes to keep a single variable or a single simple value on one side and to keep all your math on the other end. Left side being pretty conventional to keep a single variable. But that said, I think conceptually, at least in this case, it kind of makes sense that we want to think in terms of, okay, what's the right edge of the ball? The right edge of the ball is the middle of the ball plus the radius plus being to the right. And remember too that we can actually use helper variables to label this in the code so we can remember exactly what we're trying to do. Int ball right edge equals the center of the ball plus the ball radius. Int ball left edge equals the ball's center minus the ball's radius. And now in the olden days, we may not actually want to do this if we were writing programs for a non-smart handheld phone, or if we're writing programs for a 1980s computer. We actually may not want to create variables just for this purpose to label in our code. There's a minor performance factor when you do this. In a modern machine, which can do literally just billions and billions of calculations per second, it is definitely not a problem, and you should err in favor more often than not of just writing readable code, even if it means creating some new variables or whatnot. Likewise, over here, for the y, we want to account for the not just the center point, but the top edge and the bottom edge. Ball top edge equals the center of the ball minus ball radius. And you got to be careful about, let's see, remember I want to do the bottom edge first. There I was. And we want to add the radius. Because what we want to be careful about is to remember that positive y is down. When we use these labels like bottom and top, because the variables are arbitrarily named, we could get this wrong in the code and how we name our variables. Everything will work fine, but it might later mix us up. So you want to be careful about that. Ball top edge is going to be ball y minus ball radius. And if ball top edge is less than 0, then we're going to reverse its movement. And let's see if that worked for us. I believe that it will. Yeah, you can see there's a lot more satisfying. It feels a lot more solid because it's not letting itself go totally off the screen like it previously was. Now, if we make that ball bigger, so this will help accentuate that what we did worked, but I'm getting up to a problem that we're going to have to deal with. So here we have a bigger ball, and again you can see it's staying much better on screen than it did when it only behaved based on the center. Okay, but let's put this back to 70s and 100s just to get it working. And now, so you'll also notice that we have this 7 all over the place for ball move X and for ball move Y. We have -7 here and +7 there. So if we wanted to change the ball's speed, for example, let's say we change this to 18, that change will only last until it hits any edge. Because the way we're handling collision detection is we're not flipping its heading, instead we're just setting it to a negative, we're setting to a positive of a certain value. Now, there's a few ways we could do this. Let's say we could preserve that value by, instead of saying ball move X equals -7, we can say ball move X equals negative ball move X. So if we were heading to the right, it'll now be left. If we're heading to the left, it'll now be right, which means we can actually use the same expression for going off the right edge and going off the left edge. Do you see how that works? So if we're going off the right edge, and we're going, if this previously was a positive value, it would become negative. If we go off the left edge, if this previously was a negative value, it would become positive because of that negative. -1 times a negative, of course, gives us a positive again. And do the same maneuver down here. Remember, both become negative ball Y because it's the negative of what it was, which means if it was negative, it becomes positive. This will preserve those speeds. So now if I come up with custom speeds for X and Y, it'll preserve those speeds as it handles its movement around the screen. So where this can become a problem is if we start off, let's say, the right edge. So our window, don't forget, in size we set it to 720. So if we put the ball at 700x, it's going to start overlapping the edge of the screen because it's 70 in diameter. And now the ball is getting stuck over here. Because what's happening is the ball is partway off screen, it's flipping its speed, moving down, it's still partway off screen. Remember, they're only checking the right edge. And as long as the right edge is off that screen, it's going to keep moving its heading left to right, and it got stuck over there. Even if we didn't start there, if our ball decelerated, the same problem might happen, where it would be slowing down, it would go off the screen, reverse its speed, but also be losing speed constantly and not move far enough to get its right edge off the side of the screen, and it would once again just get stuck over there. And the way to check for this is that we can add an additional check to ensure that we only change the ball's speed if it's heading a certain direction. So if the ball is off the right edge of the screen, if the right edge of the ball is off the screen, and I'll show you here how to combine these in a second, but we can nestle conditionals, and if the ball's movement is positive, is greater than 0, then we're going to reverse its speed. Does this make sense? So if the right edge is off the right side of the screen and we have a positive ball movement, meaning we're moving to the right, which I guess for your camera is going to be this way, then we're going to flip the speed. Otherwise, we're going to ignore it, and this will ensure that we're not going to get stuck on the edge like that. And that should have been all that needed to happen to keep us from getting unstuck on that single edge. Now, whenever we have nestled if statements like this, if this has to be true and also this has to be true, there's a special way to write that with if statements. I'm going to cut that section. Use a Command X on Mac or Control X on PC. If we use double ampersands, this means and also. So if the right edge of the ball is off the width of the screen, and also the ball is moving to the right, then flip the ball's speed. We'll do the same check here. If the ball's left edge is off the left edge of the screen, and also the ball is moving left, flip the ball's speed. Otherwise, say that we're off the left edge of the screen, but the ball is moving to the right, then don't flip the speed because it's helping us get back into the sort of visible area. We'll do the same checks here. If we are off the bottom of the screen and our movement is taking us further off the screen, then we're going to reverse it. If we're off the top of the screen and our movement is taking us further off the top of the screen, then we're going to reverse it. And these are checks which, if you don't have them, you're going to find yourself in certain situations getting your ball, say, stuck on an edge. With practice, you learn to account for the fact that, like, well, okay, well, these are just things that we need to do to keep the ball from getting stuck. It may be weird or awkward at first to see these, especially if you haven't run into situations where they're going to be that important. It's going to happen, so I just want to introduce it now rather than later. so we didn't leave a glaring hole there. And now we can have a much larger ball without concern for will it get stuck on an edge. There it is. Anywhere we start. In fact, let's see here. We could probably even start off the screen. 50? Oops, I meant to say position X, let's say 1,000. And it'll take it a moment, but once it gets back onto the screen, it'll always come back onto the screen and stay there because of the way we've handled the checks to ensure that if it's moving back onto the screen to not reverse its speed again. So this has been the ball bouncing example. Next up we're going to be showing how to improve this in terms of organizing our code in such a way that's going to let us have multiple balls in an array. Because right now if we want to have a second ball, it's going to involve a lot of code duplication, which is something we'd really rather avoid doing. Actually though, before we do that, I do want to introduce one more thing, and that's writing a function of our own label. So what we've been doing so far is leaning on void setup, void draws being functions that when we just create them, processing knows when to call them for us, and then calling existing functions that are built into processing API, like background, like ellipse, like rect, or size. We can write our own as a label, and so you see all this awful code we have that handles the ball's movement and the checks against the edges. Well, so first of all, let's organize that a little bit better. So here we have the Y movement for the ball. Let's put those together here, just so then we have all the code in one place that handles the edge checks. We can make void ball move as a new function label. Notice this isn't changing color because it's not one built into processing. We're just authoring this. I'm going to take these two lines of code, put them inside of ball move, and when I take this same label and I call it, when I call the function is the terms we use, or the method, if it's through the Java term, then what happens is when the code gets to this point of execution, so it redraws the background with the bright blue, or the solid blue, gets to this line, it moves into handling top to bottom of the ball move function. So then it does this line, and then it returns execution flow back to draw, continuing on after ball move. Just like I said earlier, it didn't matter where we define setup versus draw. If I take this ball move function and I cut it with Command X or Control X for those of you on PC, and I move it down here, it's still going to work. Do exactly the same thing as it did before. And likewise, so we've got all this awful code in one big chunk for ball collision. I'm going to Control Command X to cut it. Ball edge check. So what I'm going to call this new function. Say void ball edge check. I'm going to paste the code into there that I cut. So ball edge check is defined as each of these temporary checks for the edges against the sides and to see which way the ball is headed. And I can even do this for one line code. So here we have this background call that's blue. If I want to make this something called clear background, let's say erase the background, and make a function called void erase the background. We'll explain the voids more in the future, but for now, they're something you're going to put there when you're writing a function. This just basically lets me relabel what that one line of code is. It's almost like commenting it, you know, because we could have just put at the end of it, erase the background. But what's nice about this is that if we suddenly have a fancier way we want to handle it, if we want to make a fade effect, if we want to draw an image there, if we want to render a map that has certain structural information in it, then we could put that within the function, which we know has to happen first. And by naming it erase the background, we remind ourselves that this has to happen before we do anything else, because if we put draw code in a different order, we wouldn't see it. So for example, let's do the same maneuver here for drawing the ball. So I'm going to cut that, ball draw, void ball draw. We really want to stress once again that the order in which these void functions are defined it doesn't matter. They function really as islands, and only when they get called from draw or from setup does it suddenly happen that it jumps to where the ball move code is defined and is going to handle those two lines of code and then return execution flows, how we describe that, back up here to the next line, ball edge check. It's going to do the edge checks, come back up here, go to ball draw, then it's going to do the ellipse call. And so after all this code that we've been writing, make this a little smaller, slow down the ball, give it a more reasonable position to start at, just for kicks. The program does exactly what it did before, but consider how much easier it is to look at void draw now as compared to how it did only moments ago before we reorganized our code. Now, draw is pretty easy to look at. We erase the background, we move the ball, we're doing the edge checks, and then we're drawing it. It's pretty straightforward. You can easily read that. And again, if we wanted to change how we draw the ball, so instead of using an ellipse, if we wanted to have a fancier shading effect, if we wanted to load an image and use an image for the ball, we could change the inside of this function and not change the process of our main draw loop, or our main draw function up here. That's happening every tick or every cycle of the program. Another thing that we can do, well actually let me illustrate one last thing. So if we change the flow order, if we draw the ball before we erase the background, we will not see the ball at all. It's there, but remember that erase the background is drawing, making a call to background, which covers the entire screen in blue. So it's drawing the ellipse, then it's drawing everything over in blue, then it's moving an edge check. So the ball is actually here, it's just invisible, and print lines would confirm that those values are still changing like they did before. But it's something to be careful about when you're handling draw order, that if you draw a background after you draw anything else, you're not going to see it. You're going to wonder, where is it? Why isn't it working? Why isn't that graphics code activating? It still is. Oops, sorry about that. It still is. You're just erasing it before you get a chance to see it. Now, one last organizational move that we can do, and this is going to get us one step closer to where we're going to better organize our code into classes, is we can create a new tab in processing. And processing, the notion of a tab is really just a file. So I click on this arrow here and go to New Tab. Now it gives me a prompt down here in yellow, asking me to name it. I'm going to call that tab Ball. And we could define a class here, so we're going to do soon. But until we do that, we can actually just take all of our ball-related code. There's our variables for ball. Our definition of functions that relate to ball. So I'm going to put ball draw over here. I'm going to take ball edge check and ball move, both of those. Put them over here. And these basically, the way processing works is just slamming this file into that one and treating them both as one big file together. But for organizational purposes, this now means that I can keep all of my ball code to a degree separated out into this other file, this other tab. And this one, we can keep things simpler and just have our void setup, our erase background call, and the calls to the ball functions. So once again, exact same program functionality, except now we've got our program more nicely split up. And it may not seem like such a necessary thing to do when the ball is the only thing in our program, but as soon as there's different things, trees, enemies, decorations, particle effects, it's going to be really helpful to be able to isolate into separate tabs different things about our program and the code that handles them. So that way we can not have to think about all the other stuff when we're dealing with one individual part at a time. This process here, in which we take code that already worked, and you'll notice we actually spent a reasonable amount of time rearranging it in a way that still works and does the exact same thing, is called refactoring. And refactoring is an extremely important part of programming. Oftentimes, while we're especially making an expressive or creative application as opposed to following a spec to write a compiler or telecom software, we're writing code and we're kind of figuring out what we're doing as we're doing it, so there's a lot of experimentation, there's a lot of trial and error, there's a lot of hacking in terms of the use of the word, which implies that we're sort of unplanned programming, sloppy programming, if you will. You can do that for a little while, you can do that to a degree while you're experimenting, but then in order to move forward, you want to have a cleaner foundation to build from. You got to be able to organize yourself to move forward a bit. And that's just where you take a little bit of time, pull some of your functionality out into functions that are named appropriately. If you have any silly variable names that you've changed the use of them and they've become outdated, you could rename those variables and make sure that they are consistent across everything. By the way, capitalization matters in programming. So if like we did a find and replace here on a variable and part of the variable name appeared somewhere else, it could cause us problems. Just to say, be careful about capitalization in variable names, and if you do find and replace, do not ignore case. You'll come to regret that later. But this is called refactoring, a very important part of programming. It's just cleaning up our code to make it do the exact same thing it already did, but having better, nicer, cleaner code to do it for us. The last thing I'm going to call attention to in closing for this example tutorial, if you're finding that this is just not a fast enough pace for you, that really you're comfortable enough with programming, or you're just really clicking with you so easily, you feel like I'm going too slow for you, a great asset in processing is if we go to the open, we can click on examples, and that gives us a series of Java examples about how to use arrays in processing, how to access the camera information, changing color, accessing external data files, all kinds of things that are going to be helpful to know how to do, working with images. And these are great examples that are built into processing. So again, if you find that you're just kind of bored, if you're chomping at the bit, you want to do more, there's a particular thing you're interested in doing, right? Handling input, well, click the open button, go to the examples. You'll find all kinds of examples of using the mouse, using the keyboard, which we're going to get to in this series too, but that's another way you can kind of shortcut to learning at your own pace, whatever happens to interest you for the kind of applications that you're interested in writing. So that's it for now. I'm going to follow up soon with another video. We're going to start to introduce classes and how we're going to better organize our ball code. An array list rather, so we can have multiple balls on the screen at once. And we might also start touching some input in terms of not just mouse position, but checking mouse clicks and keyboard buttons. Also going to add some text to the screen coming up soon, so it's a very useful thing as well. Thanks for tuning in. Hopefully I'll see you again soon on the next video. Bye-bye.